Okay, so welcome back, everybody. I see that we still have quite a few participants. Thank you for staying with us. I hope you had a good break. My name is Bruno from ID Quantique, and I am basically chairing this session. We will start with Sébastien Krafft from Pelerin, who will talk about quantum key distribution in the blockchain. That's a very interesting project we're doing in the open QKD framework with our partner Pelerin. So Sébastien, the floor is now yours.
Thank you, Bruno. Let me just share my screen. Okay, so let me introduce myself first. So I'm Sébastien Krafft. I'm the VP Engineering at Pelerin. I've been working on this project for 3 years now. Little bit of my background. I did engineering studies in France, and I've been working for more than 15 years now as a software engineer first, and then as an IT consultant in various industries, mainly logistics and banking. So Pelerin, what is Pelerin? It's a Swiss fintech company that we started 3 years ago. The project started 3 years ago. And we mainly specialize in asset tokenization and digital compliance. And we aim to develop solutions to basically bridge the traditional finance and the new economy that we envision, which is the token economy. In the long term, we have the ambition to establish a bank in Switzerland that will be full reserve, meaning that we will not have do loans on our balance sheet, and it will be a safer bank. So a bit of use case at Pelerin. So tokenization means use of the blockchain. So we use blockchain in 2 different products at the moment. So we have a framework to tokenize at the moment companies, and basically this framework would allow us to tokenize any asset on the blockchain. So any asset will be equity, bonds, funds, money. You probably heard about stablecoins, like I think the most known one is USDT, which is basically USD on the blockchain. And we have a few projects to tokenize non-financial assets as well. So we have a project to tokenize horses, for example, or art or intellectual property. So that's the kind of project that we can do at Pelerin. And the second product that we have is a wallet, because at the moment we saw that it was too complicated for individuals to manage their own keys and to manage everything. So we are trying to reduce the entry barrier, so that people can use our services in the same app, and they don't have to change from one app to another. So basically, this wallet is an entry point to decentralized finance. You probably heard of DeFi. And we provide cryptocurrencies exchange as well against fiat currencies. And as this wallet is a non-custodial wallet, meaning that the user is managing or is responsible for their private keys, then we need to put in place some solutions to store the keys, or to have backups for the users that would be non-tech savvy enough to do it on their own. Of course, there will be more use cases in the future. Basically, what we want to do is use blockchain as a back office for the whole bank. So there will be a lot more to come. So what's the relation between blockchain and public key cryptography? So basically blockchain, every wallet has a public key and a private key. So the public key is what you can communicate to everyone. It's used to receive funds. It's used to identify you on the network, at least publicly, and it's used to prove or to track the transaction that you did. And as opposed to the public key, you have a private key, which is there to sign the transactions, meaning prove that you own the public key and prove the ownership. So this private key should never be shared, of course, and that's why we decided to test this product that we call the Quantum Vault and to be part of this Open QKD project. So how do we store a private key? So first, the requirement of the storage. So of course, it needs to be reliable. If you lose the private key, you lose the funds. It needs to be protected. If the private key get hacked, you lose the funds. Tamper-proof. If the private key got corrupted, then you lose the funds as well. And it needs to be available because, of course, you want to be able to exchange your funds or move your funds from one place to another whenever you need it. So there are. I will just try to describe the solutions for individuals and companies because the type of solutions are a bit different. So the solutions for individuals. So it's mainly non-custodial wallets. So like mobile apps, apps that you would have on your computer and things like that. But the main friction point in this kind of wallet is the backup. Most of the people I know are doing backups. Mainly they do screenshots of the private key or the seed, which are stored on the cloud, which are stored electronically, or if they don't do screenshot, they write it on a piece of paper and then they lose it. And basically, if you lose the key, you lose the funds. That's the same thing with hardware wallets. You have less risks around hacking because the key never leaves the hardware wallet, or at least once when you just initialize the wallet. But the backup is painful as well. And most people I know have already lost one or two keys. They didn't lose that much money, and I did the same mistake as well. And you have custodial wallets or custodial exchange. So you probably heard of Coinbase, which is one of the most known wallet or exchange provider in the world. The main issue with this is around trust. So there's a sentence in the crypto industry which says, or in the crypto community, which says, "Not your keys, not your money." So meaning, if you don't manage your keys and if you cannot be 100% sure that you can withdraw your funds whenever you want without any third party, then it's not your money. So that's another problem for the custodial wallet. And for the companies, it's a bit different. So the companies, they used to manage Vault and HSM. So the backup problem is something they can manage. Of course, it's not easy. But there's one thing with Vault and HSMs is that it's not practical enough to be able to sign a transaction whenever you want and upon request. Most of the time, people have to go in a data center. They have to be physically next to the device, or they have to be physically in a secure zone next to the device, which makes it not very easy to sign crypto transactions. So what is a quantum vault? First, the goal. The goal is to have a secure storage, a distributed storage, and be able to sign transactions, crypto transactions on request. So the technical features of the Quantum Vault, because we are part of the Open QKD project, and we want the storage to be distributed, we decided to use quantum safe communication between the storage nodes. Then, because we don't want to have a full key on each of the nodes, we decided to split the key. So basically, M on N split across the storage node. I will detail this a bit later. We want to have a fully automated reconstruction of the key because we want to be able to sign transactions very, very quickly. And we want to have something easy and fast to operate, and which can integrate with signing workflow features so that it's ready to be implemented inside any banking grade software. So that's the schema of the Quantum Vault testbed that we are currently running in Geneva. It's been running for 3 months now. And I think the first official demonstration is planned for mid-October. So basically what we have a main HSM, which is there to, so it's this place, sorry. So it's this place, it's in the center of the drawing. So this main HSM is responsible for creating the keys and distributing it to the 5 storage nodes. So the testbed is something we decided to design the testbed with 5 storage nodes, and you only need 3 parts of the keys to reconstruct the full keys, so that we have the full distribution. And if one of the nodes is offline, or 2 of the nodes are offline, we can still reconstruct the key very easily. So the main HSM is there to create the keys and dispatch it to the storage node. Of course, this HSM is linked to a QRNG device that will provide entropy to generate the main key. So when the key is created, the key is split into 5 different shares that are distributed across the storage nodes. So thanks to our providers, CERN, Safehost, Equinix, IBM, and SIG. And if you try to hack one single node, then you will not have any access to the key. Basically, you would need to hack 3 of the 5 nodes to have full access to the key. When we want to sign something, then we have an API which will instruct the main HSM to recall the keys. So basically, it will recall 3 of the 5 shares, and it will reconstruct the full keys, sign it, and delete it. So that if you don't know when the key is present on the HSM, then you cannot have access to any of the key. So if you know what you want to target, basically the key will not be on the HSM. It will be distributed across the storage node. Quantum Vault technology. So generation of the keys, quantum RNG for real randomness. That's one of the things we wanted. IDQ is providing the QRNG chipset. So basically it was very easy to integrate. The keys are split using Shamir secret sharing scheme. It's a well-known algorithm to split the keys. And the distribution of each part of the keys is protected by QKD. So we have if I go back to the previous drawing, we have QKD links between the HSM and each of the storage nodes. So basically, we have 5 QKD links, and we use these links to exchange keys which will secure a one-time pad, also one-time pad encryption keys that we will use to transmit our secrets. So basically, with this system, we can say that we have information theoretical security, and even if we have like quantum computers or anything, it will not be possible to attack this kind of technologies. Of course, there will be other attack vectors, but not on this specific area. So how do we access the keys? So that's what I said earlier. It's recomposed for signing in the HSM, deleted after use. And what is good for us is that there's a complete split between the access and the storage. So if for any reasons your HSM is not available, then you can remove it, put another one in the, replace it, just resync everything, and you have a system that is ready to be online very fast. And one of the things that we wanted is that it can be easily integrated with banking grade access control. So basically, on top of it, of course, you have that solved the storage part, but you still have the workflow part. So you will not have the same workflow if you want to sign a $1,000 transactions, and if you want to sign a transaction that is worth multi-million dollars. So that's what bank already have. They have some kind of systems. So we want it to be designed in this way. So the main advantages, first one, unconditional security with the QRNG and the information theoretical algorithms. We don't need any full backups. So the backup is integrated into the system already. So the keys are, you don't need, if you have an HSM that is storing your keys, you will need a full backup of your HSM somewhere else. So basically you have two places where you can be hacked because the keys are fully present at these places, which we don't have. And we have high availabilities, that's what I said earlier. As the storage is distributed, if one node is offline or if two nodes are offline, then we can still reconstruct the key, and we are basically network independent. Of course, if all the nodes or if the network is offline, if the full network is offline, then we don't have any access to anything. But we assume that it will not be the case. For now, QIDiS is having something like a range of 50 kilometers, so it's enough for what we need. Of course, whenever we have a full QIDiS network working and having more range, then we can distribute the nodes in let's say other countries or other geographical areas. It's not in the slide, but the reason we wanted to do it is to basically use it internally at first to secure our own keys. So basically the keys are the one that we use for the smart contracts and the one that we use for the funds. We intend to use it to provide a backup service to our users. So all the users of the wallet at the moment would have the option to get their keys and secure their keys on their own, or delegate the backup of their keys to Pelerin. And in the future, what we could imagine, and for now the product is not ready, but what we imagine is to provide this kind of vault as a service. So we will operate all the QKD infrastructure, all the vault, and then provide like quantum vault as a service. That's something that we envision to provide in the future. Thank you for listening. If you have any questions, feel free to ask it.
Okay, Thank you very much, Sébastien. So I think I didn't tell everybody very clearly as for the first session, but if you want to ask questions, you have the Q&A at the bottom, and feel free really to use it. Still now, we have a few more minutes. So if you have any question for Sébastien, please use it right now. I have one question I wanted to ask you. You mentioned that many keys have been lost. Do you have any, I mean, this is not directly linked to the vault, but I think it would still be of interest for all of us. Do you have any clearer numbers or something? For example, how much of the Bitcoins are still there and how much may have been may just have disappeared somehow? Do we have any idea of how many are inactive? Is there any way to find it?
I don't have the full numbers here, but last time I checked, it was something. So the number of Bitcoin in the future, the number of Bitcoin will be 21 million. And last time I checked, it was something like lost keys and act keys. I think it's something like 1 million of Bitcoin that have already been unrecoverable, like
Okay.
definitely unrecoverable.
Okay, so it's already significant, let's say, so that storing these keys is really an important step, really, to make sure that this doesn't happen to your money, for example.
Yes.
Okay, so we have two questions I wanted to ask. One you briefly touched, but I think it's people want to know a bit more. What is the authentication procedure to ask the HSM to reconstruct the key? So you said banking grade, but maybe this is not very clear for people. Can you explain a bit?
So for now, in the current proof of concept, we have certificates. So basically, the HSM would contain a private or a certificate that would authenticate to all the nodes. Of course, the certificate is not the same for each node. For each node, we have a specific pair. But we are working on some other solutions to be fully quantum computer secured. Let's say secured.
Okay. Another question is how complexity can increase with the increase of nodes. So is it something scalable somehow?
So far as far as the tests have been done, so the first test that we have been doing were on 3 nodes, and you were only needing 2 of the shares to reconstruct the keys. So far, everything seems to be fine, and within 10 minutes we could go from 3 nodes to 5 nodes. So it's pretty scalable. Then that's a very good question. I think the question is, can we do it with 50 nodes? That's a question I don't have at the moment because we don't have the right infrastructure to test it. But most likely this would be something possible.
But would it take much longer to recover something? When, let's say I got 50 nodes and I need 30 out of 50 or something. Is there a need for that actually? I mean, that could be also too much.
That's a good question. I don't think there's a need for that. For us, we thought that 3 on 5 would be enough, at least for the asset we have to secure. Probably like 8 out of 10 will probably be the maximum security needed.
Yes, or we could even envisage maybe a case where you have enough nodes, and depending on the security, people could pay a bit more to have the key spread into more nodes or less nodes. Let's say you could, depending on the key value, for example, you could choose something. You could choose the right level of service. This goes a little bit into what you said about key as a service, really.
Yes, the pricing model is very open.
I see. Okay, so I have one question for me, which is you may not be able to answer that, but I'm very intrigued with what is called homomorphic encryption. And so you mentioned that you take your key, you spread it, and then whenever you have to do something, you have to bring them back, basically, to reconstruct the key and then use it. And homomorphic encryption is something that people are trying to develop, which will enable not to do that, and maybe work on the keys even though they are still in the storage node. Can you comment on that? Is it something which is possible or not at all yet?
No, so it's a very like cutting edge domain of the research at the moment, but technically this could be possible. So basically, homomorphic encryption is being able to do something with the data being encrypted without decrypting it. So that would be something that we could use. The good question is whether we need QIDiS for that or not in the future. Because if you have homomorphic encryption, then depending on the algorithm, you don't need to secure your link.
You may still want to be able to send your keys in a secure way, but
yeah.
I don't know. Okay, it's an open question, so that's a good one.
Yeah,
actually.
but it's still a cutting edge. It's still a cutting edge domain in the research industry. But technically, that could be something we could use.
So there is no true homomorphic, something which can be used today. You don't know of anything like that so far. Or you don't think it exists.
So far, no. I know that there are some products who it's not homomorphic encryption, but it's a different thing where the key is not generated in a single place, but it's it's already generated distributed, and it's never recomposed again. But from a scalability point of view, I don't know if this is very scalable. The last reports I read were that it was pretty slow to generate the keys, like something like 4 or 5 minutes.
Okay, so that could be okay. So we'll leave that for next year's talk when we'll talk about homomorphic on quantum. I think we need something cutting edge every year. So thank you very much for your presentation, Sébastien.
Thank you.
And I think we can now move to the next one, which is almost from Sébastien. It's Jean-Sebastien Pegon from ID Quantique. And Jean-Sebastien, if you are with us, please, the floor is yours.
Yes, thank you, Bruno, for this quick introduction.
I'm sorry, just before I let you talk again, if you have questions, please do ask them on the question and answers, and we will make sure we answer them by the end after the presentation. Thank you.
Yes, thank you. Thank you, Bruno. Thank you, everyone, for attending for this last presentation of the day before the weekend. So I will present one of the deployments that we did, the first deployment we did as part of the OpenQIDiS project that was presented earlier today. And we performed this implementation with SIG, a partner that I will present shortly, and with Adva, a network provider. It is running since March 2020. And unfortunately, I will represent SIG because they could not join us today. So they had a member of SIG had a personal issue. So I will present the slide that we prepared together, and I hope I can answer also your questions. You will see it's a fairly simple use case that we present. It's a point-to-point QIDiS connectivity scenario, and but it's usually the way customers start, because you usually start simple, and it allows to secure data centers, but also eventually headquarter sites to a local cloud or data center. So it's a fairly common use case, and you will be able to ask your questions online as you did before. The one question that we had last year attending ITSA with Dacoso, with Thomas actually, was is it really true that quantum communication exists, and is it true that we can already implement it? So that was really an interesting question that we had several times. So that's why I think it's important to show real real scenarios and real deployment that we have done. since already 10 years in Geneva, but it's accelerating clearly with public but also private projects. So we're looking forward for that. So quickly a few words about SIG. They are the local, for those of you that I saw on the panel that are coming from foreign countries. You probably don't know SIG, so it's the local utility company here in Geneva. They offer 4 main services. So energy supplier with a large network of more than 4,000 kilometers, water supply for production and distribution of water in Geneva, waste treatment. So it's a large factory treating 220,000 tons per year for 20,000 accommodations. So it's a local treatment. And the topic that we're going to address more today is, of course, more their telecom and optical fiber part, because they roll out over the years a quite dense fiber optical network. It's actually one of the most dense network in Geneva, connecting 80% of the population. So as you can understand, SIG has several interests in using QKD for especially securing critical data, but also leveraging their telecom network, as you will see. For those of you who attend previous presentation, you understood that there are 3 main pillars in what we call starting and the quantum safe journey. So you heard about Axel and mentioning several use cases about quantum random number generator. We discussed and presented also how the crypto algorithm are evolving, and that it's important to keep an agility and to have an agility on the crypto side. And now we concentrate on quantum key distribution scenario. So as I will present, so the basic idea of SIG was to improve the security level of the data transfer between data center. They have a primary data center and a secondary data center. This is quite common, of course, in the telecom world, where you need to back up your data, and they do the backup every night. So clearly there are lots of data that are transferred between the primary and the secondary data centers, and they anticipate the need of using a higher security than the security provided by legacy advanced encryption solution. And they wanted to take the opportunity of OpenQIDiS project to implement quantum cryptography and quantum security. The results clearly is what we see, as you understood, for many customers. Clearly, the objective of quantum cryptography is to secure data over the long term. So it's not, of course, necessary if your data validity is 1 day or 1 month. As soon as you're talking 5 years and more, you understand that probably it's a good idea to think about how to improve the security level of your encryption. That's the result that we got. So this is an overview of the scenario, and you understood that the weakness that we address here is not really the encryption itself, because we still rely on AES-256 in this scenario. But what we solve, the weakness that we solve is the potential weakness of RSA that was recognized by NIST, as you know, already a few years ago. And today, clearly, the RSA is used to distribute the symmetric key between the data centers in this scenario. And this is this weak point that we solve thanks to quantum communication. So you understood that quantum communication cannot be eavesdropped without modifying the information. So we add a communication channel, which is the quantum channel. And the key transfer then is done out of band compared to the ADVA layer, thanks to this quantum communication. So the quantum channel needs a minimum of a wavelength in some cases, and here in these cases we use the dark fiber because it was available, and you will see I will present you another scenario, but clearly it has an impact on the infrastructure, but you're adding clearly a security level thanks to quantum cryptography. If we want to see a representation, a physical representation of how it looks like, on the top you see the ADVA devices. So it's here the FSP 3000 we used with the 5TC card, and the 5TC card is actually a 10 gig card which will perform the AES-256 encryption. And the idea then is to clearly connect the QKD nodes on both sides, thanks to a standard interface, as mentioned by Thomas, if you attend. So there is an ETSI proposal to use this REST API interface. So the main advantage is that any vendor supporting this API, for example, can request keys to a QKD device. And here we have been using the Sudbury 3 product, which can support up to 2 quantum channels in one chassis. Here we use 1 quantum channel, and the service channel also between the devices. So this is the representation of the design that was deployed, and it's really a typical scenario that we see in different with different customers rolled out globally. So the advantage of using quantum keys is that you can add quantum keys to existing encryption mechanisms. So you don't need, and that's also a question that we have sometimes, you don't need, of course, to replace your existing encryption solution and network vendor. We spent a lot of energy to actually interface and validate the interoperability between QKD nodes and third-party network devices. And then the QKD key is combined with a standard session key that can be exchanged by Diffie-Hellman, for example, or SA. So then the keys are mixed and XORed so that we create what we call a super session key that then will be used for the encryption. So it's adding an extra layer of security, and then you can combine the keys. Then you can decide to run 2 modes frequently. So it's based on the network vendor decision, but here you have the possibility to decide that if the QKD device, if the QKD key is not available, then you continue to encrypt using your Diffie-Hellman key. If the QKD key is not available, you can also decide to stop the communication if really it's critical for your security level. And then the interesting part, at the network device level, you can decide the frequency at which you request keys to the quantum node. So it's a parameter that can be adjusted, like here in this example, between 10 seconds and 30 minutes, typically based on the line speed. So if it's a 100 gig speed, you have more data exchange and you want to increase the key rotation period. And then the key is requested and refreshed automatically by the ADVA device. You will see several, there's actually several advantages of using quantum keys, not only the fact that you transform an existing encryption of AES-256 to be quantum safe. So that's clearly the main advantage. But you also have the ability and to use quantum random number generator for generating keys. So the keys are probably random. You don't need to manipulate keys, so there is no human intervention or and potential errors. The keys are automatically refreshed, and you can decide, as I discussed earlier, the key rotation period, meaning that depending on the volume of data and the criticity of the data, you can adjust the key rotation period. And we discussed, of course, to go down to the second. It's not a problem as soon as you have enough keys for your applications. One also question I wanted to answer is the ability to use a single pair of fiber for the quantum channel. So clearly the preferred method, if you want to reach to have the longest reach, is to use a dedicated fiber for a quantum channel, because there are perturbation of classical communication and on the quantum channel. So the preferred way is to use a dedicated channel. But if you have constraints, availability constraints of the fiber, you can combine the quantum channel into the same fiber than your classical communications. In this case, we use a separate band. We use the O band, so 1310 nanometer wavelengths for the quantum channel. So the distance is reduced. So let's say from 100 kilometers, it may be reduced to 40 kilometers. But it of course allows to use only one pair of fiber. And the quantum channel is unidirectional from Alice to Bob in this scenario. So we use the TX fiber to add the quantum channel. And on the RX side, there are only classical communication going through. So you can use standard WDM devices to implement that. We have implemented it with SIG as well. So this is a proven and method to design, let's say, to roll out quantum key distribution. The next point is, which is a very important one, is of course Advise is really a strong partner, and Dacoso as well when we deploy solution together, especially on layer 1 using layer 1 encryption solutions. But we also work with Thales, especially on layer 2 for MaxSec, and now also as part of OpenQIDiS. We implemented a layer 3 scenario. We have been working already with ABB, now Hitachi, also on their MPLS EQ1 card. So you can, especially use in critical infrastructure. So this is an interesting scenario. ABB is also using the QRNG chip into their encryption card. So they are inherently benefiting from the QRNG and quantum random number generator for the key generation. But you can combine it with QKD. And on layer 3, which is commonly used, of course, IPsec, tunnel, VPNs. So you can combine, and this was done recently, Cisco devices, typically router or switches, Fortinet, FortiGate, FortiOS devices can use quantum keys. So it's very important you understand that we are adding an extra layer of security, and we want to be able to combine these keys with existing networks and existing technologies. And they also, of course, the vendors, and Cisco was really active in the standardization of an RFC for IPsec, the ITv2 protocol that was adapted to be able to use external keys. And it was a major step recognized by one of the leading network vendors Cisco, and we are really proud to work together as well. So depending on the scenario of the customer, we can adapt and use whatever existing technology which has been rolled out. As you understand, there is this Etsy API that can be also implemented in any application. There was an hackathon last year to implement, for example, the QIDiS into OpenSSL. So there is an OpenSSL version that you can find that can use quantum keys, for example. So any application supporting the REST API, QIDiS can request keys to IDQ QKD nodes. The next slide is a reminder on the topology. These points have been explained already. So the fact that you can of course extend the reach of 100 kilometers by adding another pair and a trusted node. So you have two pairs back to back with a trusted node in the middle, and then you can extend the reach. And this has been done with BT in the UK. We have been doing it as it was presented with SK Telecom for their 5G network. So you can extend with put 3, 4, 5 trusted nodes to extend the reach to let's say several hundred kilometers, 1,000 kilometers if needed. That's also what is done, for example, in China. In Chinese deployment, they did more than 2,000 kilometer deployment. So it's the same principle. And we support any topology. So the way it works in our once topology is defined, you define in the KMS management software, you define between which nodes you want to exchange keys. Of course, the encryptor need to be authenticated thanks to certificates, but then you can adjust, define also force, use a redundant path for redundancy scenarios, etc. So we support since the latest development, we support all type of network topologies, so mesh, ring, and star, for example. On the next slide, the objective of the slide is to demonstrate that once you have a link deployed, you can use the QKD devices to distribute keys to many applications. It can be different network layers, because depending on the application, you can do encryption on layer 1, but also on layer 3, for example. You can combine a scenario where you use the key for a quantum vault project, for example, and encryption. So any application requesting needing secret keys between two locations can use the QKD keys. So when you have deployed a QKD link between two data centers, you can use the keys at different for different use case. And the advantage is that, of course, the price and the cost per application then is decreasing. It's more justified, of course, if you have more than one 10 gig link like we have deployed initially with SIG. Of course, it opened the door also to service providers, and you can imagine that instead of having applications, you have different customers. If they are ready if they are trusting the QKD provider and QKD service provider, the customer can use keys, having a dedicated session, of course, and dedicated network to their devices. So that's also a model we started to work with cloud providers, so that if they deploy a QKD link between their data centers, they can offer QKD as a service or key as a service, depending on the model. So I hope we'll hear soon more about this, thanks to service provider deployment. So it's a quick use case presentation about what we've done with SIG. Of course, we are keen to take questions if you have any. And we can demo, as it was mentioned earlier, we can demo the, you heard also from Hannes this morning that there is an option with open calls to add applications and use cases to already deploy QKD links. So if you have any interest, don't hesitate to contact us, and we will see how to address your needs. Thank you very much for attending, and over to you, Bruno. I was not able to see the questions so far.
No problem. So thank you very much, Jean-Seb, for your presentation. Another use case. So people now see that QKD has really gone from kind of academic system to really very practical. So a first question I have is, since the long-term security of AES 256, assuming full-scale quantum computing capability remains an open and controversial question. I don't totally agree with that, but that's the question. Do you envision to shift into quantum resistant symmetric algorithms? So basically, if you do not trust completely AES, which the guy seems to say, Eduardo, what would be the solution?
So for sure, quantum keys can be used with different encryption algorithms. So it was demonstrated by Sébastien that it was used with for using one-time pad. So this is one possibility. Of course, you can imagine using quantum keys with in post-quantum crypto combined with QRNG. I don't know, Bruno, maybe you want to add on this question?
No, I just wanted to add that the one-time pad is really, let's say, the overall solution for all of that. I mean, if you don't trust AES 256, you can easily go to one-time pad, and you can imagine other things. But what I question a bit is the assumption that AES 256 is not quantum safe. I mean, I think the community of cryptographers would very strongly object to that. I think AES 256 is really believed to be quantum safe, since the key now is long enough, even when you have a full-scale quantum computer with Grover's algorithm. So maybe the answer is there is a solution, and if really AES 256 is not so good in proof to be to have a problem in the future, we can probably address that. Okay, another question is about what's the next step for the SIGs. I mean, you know, they have now a nice proof of concept. They demonstrate it can work. Do they have any plan to go further into real world?
Yeah, it's a good question. Thank you. Actually, the first, the link is used for production data, so that's an important point to know. And as you understand, SIG is active in different sectors, so they have a smart grid network that they want to also to consider using QKD into their smart grid, new smart grid topology that they are redesigning at the moment. They are, of course, a critical infrastructure network where the use of QKD is fully making sense, and you understand we're working with partners such as ABB to offer security for critical infrastructure especially. And the other side of the coin is that they are a service provider, and they have customers in Geneva in the financial sector for which they are providing encryption. So the next step is also to present this deployment and this use case to banks and to convince the ones that are not quantum safe yet that they can use SIG services. Why not to rely on them for managing their QKD link and QKD devices if needed. So that's the next step that we plan in November. We should be presenting especially to the financial sector.
Okay, that's exactly, I think, the role of the Open QKD project is really to demonstrate that it can be used in the real world, so that really we want to show to people and we want to be able to demonstrate what's going on. One comment, actually we're having a very technical discussion on AES 256, but since there was a comment, let me read it anyway from Mark, who on the comment on AES 256, it is also greatly strengthened by using GCM mode. The addition of the Galois field generated authentication tags add significant complexity to the system. So basically, Mark is answering Eduardo that AES 256 with GCM mode is probably quantum safe. Okay, so if you have any comment, Jean-Sebastien.
No, again, we are about, it's the crypto agility point that we mentioned. So we did not focus too much on this side, but for sure, it's important for ID Quantique as well to follow on this side. And we are following with our crypto experts. So let's use the best encryption algorithm that is available at a given time. Also possible to increase the key size of AES. Since Groover is reducing the complexity only by 2 from AES. So clearly we see still some customer using AES 128. So the recommendation, and especially also in the 5G world, is to use AES 256, for example, or 256-bit keys. So they are effectively, it's not only about using QKD, as you understand.
Yeah, I think that that's a really good point, which you made clear, and maybe we can emphasize this again, is that security is not a single, is not coming from a single algorithm or a single solution, and you will have probably to adapt to fit every single case. We have been discussing a few. There may be something totally different with yet other solutions with QKD on other algorithms or whatever. I think it's interesting to see that. Okay, since I don't see any more questions, I think I thank you all for your participation, and the wrap-up will be done by my colleague Gilles. So please, the floor is yours.
Thank you, Bruno. So a big thank you to all the presenters. It's a fascinating topic, and yeah, it was probably difficult to cover all the questions you might have during this afternoon session. So, but I hope that we answer most of your questions. So maybe some high-level takeaways before we conclude. So typically we have seen that the future of IT security lies in the implementation of new technologies, typically new crypto tools, and especially those equipped to encrypt data against the more sophisticated hacking techniques that quantum computer will bring. And we also seen that the risk on cybersecurity caused by the quantum computer has become real, and it's just a question of time. So implementing quantum safe security solutions will allow organizations to encrypt data to an unparalleled level. This will not only protect data from real-time hacking, but also from this well-known download now, decrypt later approach, where criminals or even states steal and store encrypted information to decipher them in the future. We also have seen that quantum key distribution combined with state-of-the-art encryption from various vendors can and should be used today to improve security on a high-value links requiring long-term security. There is actually no associated risk when implementing QKD. It's only an addition layer, very different layer of security to your infrastructure. Or it can be combined with one-time pad, for instance, to offer information theoretic security like in the quantum vault use case that we covered together. So soon enough, all organizations will have no choice but to acknowledge the threat posed by new and innovating hacking techniques and move to a better security on their sensitive data, or they risk it being stolen and exploited in the future. So bottom line, the clock is ticking, and it's time to start this quantum safe journey without any further delay. Okay, so with that, we have reached the end of this workshop. So on behalf of the IDQ, Dacoso, Pelerin, and SIG crew, we would like to thank you very much for your time today. We hope the sessions and the content have been informative and beneficial and will also help you to define and better frame your security strategy for the coming years. Obviously, if you want to discuss further any of this topic, please feel free to drop us a line at any time. You have the email address here on your screen. So with that, we wish you a great weekend, and please don't forget to keep on keeping social distancing. Bye-bye.